Welcome back. This is Fundamentals of Micro and Nanofabrication. I am Swayam from IIT Bangalore. And today we shall have one lecture on process integration. Process integration is not an integral part of this course, but it is important to understand some fundamentals or at least some practical information about how to do process integration so that you can actually make devices successfully. So we shall spend some time on it. It's very hard to teach process integration in a very structured manner. It's a sort of a learned skill. You learn it by making some mistakes and getting better with time. So the best way I have found communicating some of the concepts or some of the ways of thinking about the problem is to discuss case studies. So most of this lecture would actually just be a description of problems that students in my group face, students in my department have faced, and how we solve those problems and what can we learn from the experience. Okay. So let's get started. So what is process integration? This is actually a slide that I had in the introductory lecture way back when we started the course. And process integration, the goal of process integration is to use the techniques we have learned in each individual unit process, put them all together in a chain such that the device at the end that comes out is successful, right? It works. It requires a fundamental understanding of process details. You need to be an expert in all the process details. In when case would you use sputtering? When would you use evaporation? What is the impact on sidewall deposition? Is this isotropic? Is it anisotropic? Under what conditions is it isotropic? What is the selectivity? How much selectivity is enough? What should be the thickness of this layer? Do I need an etch stop? All of these questions must be answered by the person who's doing the process integration such that the eventual device has a high probability of being repeatable, has a high yield, and works. I mean, the device must function as per specifications. Okay. So the devil is always in the details. So have a very keen eye to the details. So we have discussed so many details in each of the specific modules, and those details really help you in being a better process integration person. But PI is still a very interdisciplinary field. It requires some understanding of chemistry, some understanding of physics, some understanding of material science, some understanding of devices, some understanding of some experience of just making things in the clean room. So it's a very interdisciplinary field, and it's as far as the jobs inside a fab go, it is one of the highest, let's say the most respected jobs. The best people in the fab tend to be the PI team, the process integration team. Okay. So what is process integration? So again, this is a slide from that first lecture. So as process integration refers to the fact that what you end up is with what you call a wafer, right? And this wafer is a sort of a patterned wafer. There is a after say 50, 60 or 100 steps, you have deposited, etched, patterned several different layers, and you have ended up with this wafer. But this is still not a device. Then it needs to be cut into individual dies. Then the individual dies are then packaged into say one packaged device, and this packaged device is then put in a circuit, and then that is what the eventual person uses. So what the process integration person's job is to make sure that this part of the equation is working perfectly. But in order for this device to function at the packaged level, there's a lot of optimizations that must be done at the wafer level itself. So while the job is restricted to what is happening on the wafer, a PI person should have a very clear idea of how the eventual device will be maged and packaged for them to design the device appropriately. Okay, so that's something to remember. So if you think about it, we are able to make remarkably complex chips these days. So a typical Intel device has what, more than a billion transistors, and despite that inherent complexity, we discussed so many nitty-gritty details, and we have just looked at the surface. Each of these processes has way more complexity attached to it. This is a fundamentals of micro nanofabrication. We can do an advanced micro nanofabrication, and there would be still things that we would not cover to really highlight the details of each of these processes. So it is actually amazing that all of this comes together and the final device works. And part of the reason is that there is inherent modularity in the system. So you can imagine you as a consumer who's consuming, say, a laptop, right, who's using a laptop. For their laptop to function, the chips must function, right? The chips must be mounted on a circuit that must function. Inside the chips, there must be devices which must be designed in a certain manner and must function. In order to make that device, there must be a process integration person who designs the process to make that device. And below it is a person who's a unit process specialist, who's only, say, depositing metal, who only deposits metal and optimizes the recipe for depositing the metal. So there's so many people with so many layers of problems, right? So you start at the unit process and you go all the way up to the circuit designer. The way the system works is it's small modular. The circuit designer never gets to talk to the unit process person. Okay? All the circuit designer expects is you just tell me what is the characteristic of the device you are making. I'll not ask you how you are making the device. I will not ask you about the details of the unit process. All I care about is what is the current voltage characteristics of the device. I will design my circuit appropriately. The device engineer just thinks of the device. He doesn't think of how that device will get fabricated. That's the problem of the process integration person. And the process integration person just asks, tell me what is the unit process. I don't want to optimize unit process. I don't want to know the details of the unit process. I just want this to happen. Okay. So that inherent modularity, there is a the responsibility and the duties are very clearly demarcated, and people just talk within each other on basis of documentation, on through specifications. They don't necessarily need to all sit in the same room and discuss things through. And that modularity is very key to make sure that you get a new chip that works exactly the way you designed it to work every 2.5 years. Right? So the documentation and specification is a very important aspect of process integration. A lot of students don't keep, for example, good lab notebooks which detailed notes of how did they make the device. That's a very poor idea. That's a very poor habit. In general, have very good detailed documentation. You should make detailed, copious amounts of note of how exactly that device got fabricated. A few months, a few years down the line, you will not remember the details and you will not be able to recreate the good data that you got because human memory is failing. The only way to ensure things survive is to make sure things are documented. All right, so now let's talk about case studies. So it's a case study time. So I'll just sort of highlight an issue and then we'll talk about a couple of examples and keep going. So first thing first is that all process integration starts with some substrate selection, right? So you select a certain substrate and you decide that this is where my device will be made on. So of course you have so many options. You have silicon, germanium, gallium arsenide, and we actually went into some detail of what are the advantages and disadvantages of each of these materials. So the things to keep in mind when you're selecting the material. First, what properties do you need? If you want optoelectronic properties, if you want to make an LED, gallium arsenide is so much better than silicon, right? Because it's a direct bandgap material. Do you care about the mechanical specifications? If you're just making a MEMS device, you just care about the mechanical specification. But if you are making a solar cell, you care about mechanical and electrical properties. So depending on what you want, you will have to select the appropriate grade of the wafer. Is it test grade? Is it prime grade? Do you need transparency? If for some reason you need transparency, then you have to think of it upfront, right? So silicon carbide and sapphire are sometimes often transparent. Silicon is not, at least not to visible light. Do you need thermal insulation? If you're making a device that a very high power device, then thermal conductivity is hugely important. It's very important to sort of, if you can make gallium nitride, for example, on silicon, you can make gallium nitride on sapphire. You can make gallium nitride on silicon carbide. Which one should you choose? Depends on your application and specifically thermal load. Do you want single side polish, double side polish? If you are just planning to do lithography on one side of the wafer, maybe single side polish is enough. But if you are planning to do lithography on both front and back, maybe you should start with a substrate that is double side polished. So a lot of these things that will be important down the line can be managed upfront by selecting the appropriate substrate, and it will again enhance the rate of success. Right? You can always figure these problems out by making a mistake, but then you waste a lot of time, and more importantly, you waste a lot of resources. So good to have to think ahead. So here's an example of substrate selection. So this is something that came out from our group. What we were trying to do was we were trying to deposit some germanium on silicon, and then we are trying to crystallize the germanium on silicon to get crystalline germanium on silicon. Now, when we do that on silicon substrate, it works very well. So you actually see a crystallized germanium film here, and you actually see these boundaries which represent a polycrystalline germanium, a crystallized polycrystalline germanium. However, when we tried the same thing on titanium nitride, so just coating titanium nitride on top of silicon, and when you do this experiment, it doesn't work. It so turns out that the germanium tends to form droplets. Now, why is that happening? So we looked into the detail, and the detail is that during this process, we are essentially melting the germanium and recrystallizing or solidifying the germanium. And during this solidification process, during the small portion when the germanium is liquid, it is sensitive to surface tension. So on silicon, it wets the surface. When it wets the surface, it forms a good smooth layer. On titanium nitride, it does not wet the surface, so it forms globules. Now, this is a failure because the student didn't think it through that by adding this titanium nitride, would we make a significant change to the substrate? It turns out we did. So again, if you go and look at the literature, you can actually figure out that the surface energies are very different. This is hard to wet, this is easy to wet. So this was a predictable problem, but we missed it. So these are some of the things that if you think ahead, you will be able to prevent and save time. Other issue is material compatibility. So questions such as, what is the maximum material your process can tolerate? If you are doing things on a glass substrate, none of the processes should ever exceed 650 or 700 degrees C. That is the temperature at which glass starts becoming soft. If your film has aluminum, after deposition of aluminum, maybe you should never increase the temperature to more than 600, 700 degrees C, because that is the temperature at which aluminum melts. So what is the maximum temperature a system can tolerate? Whenever you heat things up or cool down, they always create stresses. Those stresses are called delamination. So here is an example of some metal layers that have gotten delaminated. Right? So is that something, is a possibility? Can you do something about, can you do some changes in your process to make sure that doesn't happen? Can you add some adhesion layers? Can you change the temperature at which you're doing the processing such that the stresses don't become so large that the delamination can happen, etc. Do the materials stick to each other, right? You deposit one film, material 1, and then deposit a material 2, and you sort of implicitly assume these two materials stick to each other. But that might not be the case, right? So here is an example. So what we were trying to do was we were trying to create a nickel grid on glass, right? So very simple process, glass substrate, and find a grid of nickel metal. So it's a very simple process. You pattern the nickel using lithography and either etch the nickel, or you pattern lithography and do a lift off, right? Both work. It's a very simple process, 4 or 5 steps, you're done. But when you actually did the process, we deposited the nickel on glass, right? But what we found was the nickel doesn't adhere to glass, right? So you start sort of see this, right? This peeling sort of thing. It's like nickel is not adhering to glass, it's sort of peeling off. And when you try to pattern this nickel that is poorly adhering to glass, it comes off from places where it should not come off. So it gets overdeveloped very easily. So the pattern that you actually get, and I hope you can see it, that some of these lines are blurred, and that they are blurred because the nickel is not there, because the nickel just peeled off. So you wanted a pattern that is continuous, but you are getting a non-continuous pattern, which is obviously bad. So what's the problem? The problem is nickel doesn't stick to glass. What can we do about it? It so turns out it's something very simple you can do. You can introduce a thin layer of chromium between the metal and the substrate. Chromium acts like an adhesion layer. Titanium does the same thing. And that allows you to deposit nickel on glass through this very thin chromium layer. So the chromium can be very thin, say 10 nanometers, maybe even thinner. And then you get perfect registration, you get perfect patterning. There is no peeling off. So again, things like this, with experience you can pick up, and you can do upfront to make sure your device run is successful. The third thing is to always think of the effect of process on the device, right? So during processing of, during any unit process, we sometimes are heating the wafer, we are sometimes exposing it to chemicals, we are sometimes exposing it to plasma. All of those things have an impact on the device, right? If you remember when we were doing E-beam evaporation, we discussed how during E-beam evaporation you can form a little bit of X-rays which can cause defects in the silicon dioxide interface, right? We discussed when we are doing sputtering is a little higher energetic process. So during sputtering, we create a little bit of damage on the substrate. So if your substrate is organic, that's not very good. So you have to think in advance of these second order effects. What is the effect of the process on the device that I'm trying to make? Supposing edge profiles are important for you. What sort of edge profiles do you want? Here's an example. So if you, it's very obvious what we have here is a dry etched hole, and this is specifically using deep reactive ion etching, the Bosch process. You can tell this is the Bosch process because you can see these rings, right? These scallops, and each of this scallop is one etching cycle. So the way that deep reactive ion etching works is that you sort of every cycle creates this one scallop, so you can go very deep, but then you get these scallops on the surface. Now the question here is this surface roughness important to you or not? If you're making a mechanical MEMS device, maybe not so much. But if you're making a laser, or if you're making an silicon photonic waveguide, then this roughness is problematic, because this roughness will scatter light and reduce the efficiency of your device. So then you cannot tolerate it. So what can you do? Maybe you should not use DRI. Maybe you should use RI, or maybe you should use wet etch. If you have to go deep, maybe you should use a combination of DRI and wet etch to smoothen the surface, right? So it's not as rough anymore. So questions like that. We already discussed effect of thermal treatment, right? So if you have aluminum already, maybe you should not be subjecting it to any anneals that are 800 degrees C. If you already have metal, maybe you should not do any cleaning that involves acid. If you are depositing, if you are in the back of the line, you should probably use some sort of a dry etch to clean organic contamination, or use solvents to create organic contamination, and not an RCA recipe, right? So those kind of things that you have to always remember. So it uses the basics that you have learned from your unit process, that for example in this course whatever we learned, you use those same concepts, but then you have to remember to apply them when you are doing the process integration. Here's a case study for what, for example, something that came up where the process affected the device. So what the student was actually trying to do was trying to study a certain metal oxide. So a lot of metal oxides are dielectrics and insulators, not very interesting, but there are semiconducting oxides. So in this case, we were looking at some semiconducting metal oxide. So that's this gray film here. Now in order to study that film, we want two electrodes, a top, a bottom. Since things are easy, students started with a highly doped silicon. So the highly doped silicon served as one of the electrode. You deposit the metal oxide, then you deposit the gold on top. You have this sandwich structure. You can go and measure the IV characteristics. So when the student did that, this is the I, this is the V, and if you zoom in here, you actually if you zoom in here, you actually see that you are flowing something on the order of 10 nanoamps of current. Right? That's a very small amount of current. And the reason for that is that, so what the student sort of extracted from this test was my metal oxide is very insulating. But it is a wrong conclusion. And the reason is that he has missed something in the process flow. So if you look at detail, right, after he did the metal oxide deposition at 900 degrees C in oxygen atmosphere, can you spot what the problem could have occurred? The problem is you took the highly doped silicon, you introduced it to 900 degrees C in oxygen. What will happen? You will oxidize the silicon. So what you have on the highly doped silicon is not highly doped silicon alone, but also a layer of silicon dioxide, and that is an insulating layer. So what he wanted was a device structure that looked like this. But what the student got was a device structure that looked like gold, metal oxide, silicon dioxide, and silicon. So it doesn't matter whether metal oxide is conductive or not. The IV characteristic is completely decided by the insulator that has been added in this structure, simply because of the way we did the processing. So what the student ultimately ended up doing was did not use silicon as a substrate. They just used FTO as the substrate. Now FTO is already an oxide, so it cannot be oxidized anymore. So when you do the FTO is a conductive oxide. So you deposit this conductive oxide at a slightly lower temperature, and you can now see microamps of current, which is what you are expecting. So the problem was not metal oxide, the problem was the formation of the SiO2. But you can come to a wrong conclusion by not thinking the effect the process is having on your device. So always be wary of it. What is this recipe doing to my device? The next issue often is equipment capability. A lot of people don't interact with the unit process specialist too much. So you should always ask a lot of questions. What is the size of wafers you can tolerate? What is the smallest? What is the largest? Can you take in small pieces? Do you only need full wafers? Can you do quarter wafers? Can you do half wafers? What is the temperature range that you allow? What is the contamination policy? What sort of films are allowed in this material? What sort of materials are allowed in this equipment? What materials are not allowed in this equipment? How do you load the sample? Is it important to do the cleaning right before the loading? Can we do cleaning 24 hours in advance, or do we have to do cleaning right before loading? So those details really matter, and that conversation with the person who's using the equipment, that could be you or could be a dedicated unit process person, is very important. And a successful PI person has a very good handle on these nitty-gritty details. Okay. So here's an example. So you can process full wafers. So full wafers are often loaded on this wafer boards. But you have very small sizes, say 1 centimeter square. Now those 1 centimeter square samples cannot be fit on this board. So what can you do? Well, you can either make a makeshift sort of board like this, but for that you have to actually create this piece of silicon and actually clean it during your cleaning step. So if you think of this problem in advance, you will clean all these accessories and create this mini boat that can hold a smaller sample. But if you don't think about the problem, then you do all this cleaning, you go to the tool, you're ready to do your deposition, and suddenly you realize you can't do that. And that wastes a lot of time, it wastes a lot of energy, and it's very demoralizing. So again, think ahead, think ahead, think ahead. Devil is in the details. Unit process usability. So when a unit process says, I have a recipe to deposit aluminum, that's a good place to start, but you should always understand it a little bit more. Okay, what is the deposition rate? What is the minimum thickness, maximum thickness? Does this unit process actually work for me? A good example, a classic example is you can deposit aluminum using sputtering, evaporation. Which one should you choose? Well, it depends upon what substrate you are depositing it on, what sidewall shape you want. Do you want conformal deposition or not? So here's an example, right? So what we are doing is, here's your silicon. It has been coated with silicon dioxide and then coated with aluminum. Now, inherent in this device design was the assumption that the silicon dioxide that is being deposited is conformal. Because if it's completely conformal, this aluminum is never touching the silicon, so it's a nice gate. Right? But the process they ended up using was not conformal. So the silicon dioxide really is not conformal. Because it is not conformal, it has a little break. And at this side wall, this aluminum can now touch the silicon. And if the aluminum can touch the silicon, it can create a short, and then you do not have a gate. You do not have a metals insulator semiconductor interface. You have a metal semiconductor interface. So these questions can only be resolved once you think it through. Like, I want to deposit silicon dioxide. I can do it 5 different ways. What is my need? Is this unit process more appropriate? Is that unit process more appropriate? And then you choose a suitable one. A lot of things, mask is often the first thing that people make when they start making a device, right? So you make a device, you make a flow, and the first thing you then do is make a mask. Now, because it's the first thing to be done, any errors or omissions made at the level of the mask really bite you later, right? So invest a lot of time and a lot of thinking in designing the correct mask. What is a correct mask? It should have alignment marks. How do you plan to align? What level do you plan to align? Is your critical dimension 1 micron? Is your critical dimension 5 micron? The alignment marks would be very different. Have you accounted for process variability? The mask that you have designed, does it require you to do a wet etch with 0.1% precision? Of course, that's not possible, right? So maybe the mask design needs to change if it requires a process to have a precision of 0.1%. If you are going to package the devices, have you already thought of how will you cut these devices into dies, and how will those dies be mounted on the actual packaging platform, right? Have you thought it through? Do you need test structures, right? A lot of people make a device. You want to make an FET, great, of transistor, you make a transistor. But if you just make a transistor, and if the device doesn't work, you have nowhere to start which process failed. Very important to have a whole bunch of test structures. something that measures the thickness of the oxide, something that measures the leakage of the oxide, something that measures the deposition of the metal, something that measures step coverage, something that measures pinholes, or something that at least tells you that they were pinholes. Some places where you can take nice cross sections, so you can cut the wafer and look at it under an SEM. So those kind of advanced what we call test structures, or structures that you need to brainstorm what problems could have happened during the process, are very important. So if you have them on your mass structures already, then it becomes very easy to fine tune the recipe, figure out what went wrong, fix it and move on. Otherwise it's a black box. You started with a wafer, you ended up with a device not working, which process failed, very hard to find out. So fix that at the mask layer itself, right? And there, of course, there are other sort of nitty-gritty things. If you want an exact rectangle, if you start with a rectangle, you'll actually get with a smoothed oval, especially if the features are small. So if you really want a rectangle, maybe you should start with a slightly different shape. So things like these, you can solve at the mask level, and by solving at the mask level, you save a lot of time down the line. So here's a very interesting case study of what can happen if the mask is designed a little poorly. And this happened in our clean room. And it's an interesting story. So what they were trying to make was something called a microheater. Very simply, what the microheater has, it's a metal filament. So you flow the current in the metal filament, and because of that, it heats up just like a bulb heats up. Just like the bulb heats up. And because of that heating, you can then heat the substrate. Okay, so that's what the microheater is, right? It's a small heater. So what the microheater actually has is there is a cross section of silicon, there is silicon nitride, and there is a metal pattern on the top. So this is what the cross section looks like, this is what the top view looks like. So again, a fairly simple device. It requires just two lithography. So on the front, you pattern the metal through a mask, and on the back side, you pattern the silicon, the hole. So you sort of cut out this hole in the silicon. So there are two masks involved, one deposition of silicon nitride, one deposition of metal, and done. So what people found was, this was the mask design that looked like on the CAD. So this is the CAD design. So you see the metal lines, you see the island, which is the silicon nitride, the island that is the etch from the backside, right? And what they were basically finding, that when they actually made the device, this grid, this metal grid is not exactly centered, it is biased. So I hope you can see that this is the membrane, and instead of being in the middle of the membrane, it's to the side. It's slightly misaligned. And it's misaligned fairly large, like the misalignment is 100 micron, that's a very large value. And the problem with this is because this is a heater, it heats. If the heater is not positioned in the middle, then it heats not uniformly, and that causes device failure. So this is a problem, this cannot be tolerated. So the question is, where is the problem coming from? So the first thing you tend to blame is, okay, lithography went bad. So we went back and looked at the equipment. Is the lithography misaligned by any chance? We did a whole bunch of tests. You can look at the figures. If you don't understand what we are looking at, don't worry about it. What the point of these tests was to show that the lithography equipment is working fine. There is no misalignment. This device was not working. Other devices that other people were making were working. So the unit process is fine. There's no problem in the lithography unit process. So then what is an issue? Again, this is again showing the misalignment, right? So here is the back hole, and the metal electrode is misaligned on it. It's not positioned in the center. Okay. So what do you think, right? Maybe stop the video here and think about it for 30 seconds. What do you think could have gone wrong? Now the hint is this misalignment was there, but it was repeatable. It was coming the same 100 to 100 micron every single time. Does that tell you something? So here's what was happening. You see, when the person who designed the mask assumed mirror symmetries, what that means, so what they designed was they designed a device that looked like this, all right? So they have the gray region which represents the back hole, they have the metal electrode. They broke it into two different mask designs. So they on one mask they wrote the metal pattern, on another mask they wrote the back edge pattern, okay? Great, nothing wrong here, everything is fine. The problem is, they ended up making a structure that was slightly biased, that was not centered. Okay? Now on its own there is no problem. This would still break into two designs, but both the metal and the gray would be misaligned by the same amount, so there would be no relative mismatch. This would still work. The problem is the way they were doing lithography. Remember, This is the design with no mirror symmetry, right? It's a biased design. It creates a biased metal film. It creates a biased back edge pattern. But remember, the back edge is done on the back side of the wafer, for which they take the mask and they turn it upside down and do the alignment from the back side. When they do that, what happens to this design? It flips. It flips. Instead of being biased to the right hand side, it biased to the left hand side. And when you now do the front and the back side alignment, you would always get a misalignment. You would always get something that looks like this. So that is what they were having. So the problem was not in the unit process, the problem was in the mask design. So things like this can happen and they're very hard to figure out. So be careful, be careful. Okay. So yeah, so they ended up making, so they realized that instead of having a design that looks like this, what they are designing is something like this, and that is what they are getting, what they are fabricating. So they fixed that problem and the issue went away. The next issue we have to deal with is the order of steps. So often you have a choice. Supposing you have say 2 or 3 lithography steps, you could probably do lithography 1 first and lithography 2 later, or lithography 2 first, lithography 1 later. You can deposit backside metal first and the front side metal later, front side metal first, backside metal later. So some of those decisions where you have an option of going one way or the other, the question comes down to which is more repeatable, which will lead to less contamination, which allows you to do the process more cleanly, which allows you to do the process more repeatably. And those are things are worth thinking about before doing an actual design, before actually doing the processing. So a good case study for what such a problem could be is the case of a microneedle. So if you look at the what a microneedle is we are trying to use silicon to make these very sharp and small microneedles. And the advantage of these microneedles, theoretically at least, is that they will be able to inject things like insulin into the human body, but without the pain. So right now, syringes are painful because there's this one macro needle that is sort of impaling you, right? And that's hurtful. But if you have these hundreds of small micro needles doing the piercing, you might not actually feel it much at all. So that's the idea of micro needles. So let's not go into the biological details, just that what we are interested in making is a cross section that looks something like this. So if you're looking from the side, what you have is a silicon wafer with several holes in it. And on the top, there are these cylindrical needles, right? So these hollow cylindrical needles. So this is the top view, this is the cross section view, and these are the ones that are actually impaling your skin when you're trying to do injection. So this is the idea of a microneedle. So it's a fairly simple fabrication process again. All you really need is 2 lithography steps. So we'll call those lithography steps the pin mask. So this defines this top needle, right? And the other is on the back side you have to do a through edge, so a through mask. So something that creates the central hole and something that creates the outside of this needle, like these 2 edges. So fairly simple fabrication process. So the question is, how would you do it? So we started making these devices in our clean room in IFC. And just like in the previous case study, we were consistently seeing a misalignment. Okay, so here what you are seeing is that the needle exposure and the through hole exposure are a little off. So instead of the through hole being in the middle of the needle, what you actually have is they are misaligned, they are a little off. Now, unlike the previous problem where the misalignment was sort of consistent at around 100 micron no matter what we did, here the misalignment was random. So in one case we say get an 85 micron misalignment, here we got 235 micron misalignment, so like completely off. Now, once again, the problem is not in the unit process. The unit process works fine. There's just something when we are trying to do this specific process that the process fails. The question is why? And the hint is, unlike before, this time it is random. So what do you think is happening? Think order of steps. So again, pause the video maybe for 30 seconds and think what could be happening in the way we are doing the lithography that is causing this. So let's give you the answer. So what you are trying to do was we are trying to do the pin mask first. So after the pin mask, this is the cross section you have, right? So you have not done the through hole, but you have done the pin mask and on the front side. And then what you do is you turn this wafer upside down, okay? And when you turn this wafer upside down, then you do the through hole mask. So now during this through hole mask, what you do is you do the alignment. So you have an aligner and you position the two together and then you start doing the exposure. Now during this alignment process, the way we hold the silicon wafer is through what we call the vacuum chuck. So you just put the silicon wafer down on a chuck and pull vacuum, and just by air pressure the wafer is snugly fits onto the top of the vacuum chamber and doesn't move. But if you look at this cross section, you notice something. This cross section, the bottom surface is not flat, right? So when you pull vacuum, it doesn't hold the wafer because the air continuously leaks through the bottom. So the wafer never sits very snugly, so the wafer moves. If the wafer can move, you can start with an aligned wafer, but during the alignment, through some random vibration, it can switch left, it can switch right, and it can move any amount. That is why the misalignment is random. So what do? Well, we realized that the issue is that the second process cannot be done after the first. So all we had to do was just switch the process. So we did the through mask first, and then when we turn the wafer upside down, now we don't have these needle type thingies on the bottom, right? We still have, by and large, we have holes, but we still have by and large a flat surface of silicon. So now that silicon surface is held tightly on the vacuum chuck. When you do the second alignment, the wafer doesn't move around, the misalignment doesn't occur. And we were with that, if you look at the slide, we were able to make perfect microneedle. So this is what a microneedle looks like in the cross section. Okay. So the order of lithography mattered, right? And yeah, this is something that you learn with experience. Which should you do first, which should you do second. The final issue I would like to highlight is issue of reliability. And often in academic circles, reliability is not given its due weight, right? The goal is to show that one successful device, write a thesis, write a paper, and move on. But the fact of the matter is, to show technology, you always have to show repeatability. You have to make the same device again and again and make sure it performs the same way. But even in academic circles where you just want that one device to work, it's sometimes important to think of reliability, because if the student is making 10 runs and only one run is becoming successful, then they're taking 10 times longer time than is required. So maybe it's worth it to spend more time in designing the process such that the reliability becomes 80-90%, so that just 1 or 2 runs are enough to get a device out, right? So the way to do that is often to incorporate a whole bunch of characterization steps while you're doing the processing. So you don't wait till the whole device to get to know that, oh, my metal that I deposited was too thin, or oh, the silicon dioxide I deposited was too thin. Maybe you should measure it at that point. So if there is a failure that has happened, you would notice the failure. Either you would do something to fix it, or you would start a new run. You would not waste all that time and effort completing the device run. A lot of times you should have multiple dummy samples. So if you have a process that requires 30 steps, that's a very precious sample, right? If it has 25 successful steps on it, it just needs 5 more to become successful. It's a very expensive and a very precious sample now. So you don't use a precious sample to, you don't use it you don't use it first time. So when you approach the 26th step, what you have is a whole bunch of dummy samples. So first you try the dummy sample, make sure the equipment is functioning, make sure the recipe is stable, make sure you get what you are expecting. Then you put your precious sample, and then you have a high probability that the 26th step would also be successful. So dummy samples, inline characterization, a lot of test structures, those are good practices that will improve the reliability of your fabrication. So here's actually an example. So what you actually see is we were trying to deposit silicon nitride on silicon dioxide. The target was that we deposited 100 nanometers, but what we were actually getting was only 94. Now that might be okay, that may not be okay. It depends upon what is the tolerance of your process. But it's very important to do these sort of measurements while you are doing the fabrication, so that you don't get a surprise at the end. With that, I think I come to the end of the lecture. So that was a very short introduction to what is process integration, what it takes to be good process integration. As I mentioned at the start, I cannot give you everything you need to know to be a good process integration person. A lot of it is learned by experience, a lot of it is learned by thinking a lot of it is by spending some time, by being expert in unit process, right? The more you understand the unit process, the better you can be in process integration. So we just discussed a whole bunch of case studies. Hopefully that you would have found them interesting and illuminating. And I'll talk to you soon. Bye.